should inform you about the two most important singularity function in circuits analysis. And firstly, what does it mean, singularity? Singularity functions are neither not finity or they not possess finity derivatives anywhere. We'll see what exactly it means. And we have the two most important functions which is connected with circuit analysis. The step unit functions, it is called also Heaviside functions, which we write as a u from t or 1t. And the second singularity functions, the unit impulse. It is the delta function. Okay. And first functions, the unit step functions, has the value equal 0 for t less than 0, and has value equal 1 for t more than 0. Okay, and this is the question: what is the value exactly at the time equal 0? So we don't know, but the physical analogy for of this function corresponds to closing a switch at time equals 0 and connecting a voltage source of 1 volt or a current source 1 ampere to given circuit. For example, this is the I put here the two circuits, and this is, for example, load. You can imagine, for example, the bulb on the ceiling, and we switch the switcher, close switch, and now we connect at the time equals 0 source, voltage source or current source to the load, to the circuit. And it is schematic, and it is the picture how this singularity function is in the time. Okay, so at the time equal 0, someone switch is on, and we have the value equal 1 before 0. And at this moment, we don't know about the value. This we know that the value is between 0 and 1. Okay, and this is another situation that we switch on at another time. The moment is equal in this situation. This situation is it is equal a. So at the moment a, it means the a seconds from the t equal 0. Someone's switch on the switch, and this is this situation that the close is equal a in this situation. Okay, and this singularity function is useful to describe signals which we are using in transformations. For example, we cannot when we use these singularity functions, step functions, you can describe this situation, discrete situation, and also describe such situation like in this picture. Okay, so for example, for these parts, we can assemble to another unit step functions. Firstly, which is go up at 0, and secondly, it is go down at the moment equal t. And when we add this first and the second function, we obtain such curves. Okay, and now we can try to find the Laplace transformation of these unit step functions. So we are using the definition for this, and I put just here this u from t and this integral, and we know that the value from this integral limitation it is equal 1. So as a result, we obtain that the transformations unit function is equal 1 by s. So we can write this, that transformation it is equal fs, it is equal 1 by s. Okay, and now we can find the transformation when we shift this unit function in the time. Shifting time is equal a, and so I, instead of this function, I put here this function, and we know about the value. So this unit shifted step function, that it has 0 for t less than a, and 1 in this range. And so we can change the limitation of this integral, and now when we calculate, we obtain this value. So you can notice that we have here and here the same denominator, but we have here another factor, e up to minus as. Okay, and now we can when we assemble this function and this function, such this picture, we can try to calculate the Laplace transformation such parts. So I put here this function, and as a result, I obtain this minus this. But instead of I have here the t. So it is the differences, and here I have the minus because of this sign here. Okay, so we know about the transformation unit step function, and now we are talking about the unit impulse function delta t. Okay, and the delta t it is the singularity, the second singularity function, which has 0 value for all time except one moment when t is equal to t0. And the second property is that we don't know about the value at this point, unit impulse functions, but we know about the integration. When we integrate these singularity functions in this region from t0 minus epsilon up to t0 plus epsilon, we know that the area is equal 1. Of course, the epsilon should be less, should be more than 0. And the unit impulse function is 0, except, as I said, t equal t0, where is undefined. We don't know about this value. It is very high, but it has a unit area. Okay, and I can try to describe this in this picture. So you can imagine here this rectangle. Okay. So sorry for this noise. And this rectangle, and here we have the coordination system, and this is the t0, and we have here the t0 minus a half a and t0 plus half a, and the height of this rectangle is 1 by a. So when we calculate the area of this rectangle, we obtain the value equal 1. But what is when we decrease the value of a? So when we decrease this value, we obtain such situation that this is thinner, and as a result we obtain one line, and this one line is delta. This is the delta. It is also called delta Dirac, and the important is that we don't know the amplitude of this. We expect this amplitude is high, so which it is represented by this arrow, but we know about the area, and an important property of delta function is the sampling property. So when we multiply this any function ft by this delta, we obtain the function's value at exactly at the time equal t0. So it is an important property, and delta t function simply samples the value of ft at this moment t equal t0. Okay, but someone can say why we need such sparse function, because it is not practical. So although we cannot produce a voltage or current signal with zero width and infinity height, in the physical system, the delta function is a convenient mathematical function for modern physical process. Of course, it is not obviously, but I try to show it. Okay, so the Laplace transform of the impulse function is from the definitions. I put here the delta function. And we obtain this. We cannot directly calculate the Laplace transform from these equations, but we can obtain this result using the sampling property of delta functions. So we know from the previous picture about the sampling property. So we know about that the value is equal just the function's value at the time equal t0. Okay, and now we can try to put instead of t0 value equal 0. So when we go to the 0 with the t0, we obtain that the value e up to minus st is equal 1. So the Laplace transform of unit impulse is equal 1, just 1. So we can also remember that when we make differentiation of step functions, we just obtain the delta functions. But I cannot write here the equal symbol. Just I put here with this one because it's not the function step functions hasn't differentiation at this point. So at this point, the real domain hasn't value. So, but from the singularity functions point of view, it has value delta t. Okay, and now we can try to using the unit step functions to describe the functions. For example, we have such functions t functions, and now we can write from directly from this function that we have the u t, it is from 0, and now I add another functions at this moment, t equal 1, but this value is changed from 2 to 1 at this moment. So in this moment I should subtract this function. At the end, I subtract these functions from beginning from the t equal 3, and it is possible to using the unit step function to describe such functions like this. And now this is the function f2 multiplied by unit step functions. So as a result, we obtain such functions. And now I can write these equations for such functions which is start at 1, and this slope is described by this factor. This factor slopes this describe this slope. But when I assemble this one and this one, I obtain this function and this. But after 1, it's going down and going down. But in this picture, I have this function is equal 0 after the moment 2, and so I have to add another functions which is start at this point. So when I add this and this, I obtain such function. So it is also possible to describe such functions with another slope, not only the step. Okay, and so we can try now using the unit step functions to describe such functions. It is the half of sinusoid from 0 to 1, and after 1 it is equal 0. So we can imagine the sinus function. So we have the sinus function multiplied by ut. So below 0 is for the time less than 0 is equal 0. And now we have another functions another sinus functions which is start at this point at this one. So when we add this function and this function, we just obtain this the first function. Okay, so now we are talking about the transform pairs. So, for example, we try to find the Laplace transform for several commonly using analytical circuit functions. For example, we have the functions ft equal t. So we can solve these integral equations for integration by parts. And when we divide into two parts, the first and the second first function and the second function, as a result, we obtain the transformation which is equal 1 by s squared. So the ft transformation is ft equal t is equal 1 by square s. Okay, and it is also possible to find the Laplace transformation using for the sinusoidal functions. In this case, it is a good idea using the Euler equations, and so you see here the sinus omega t. Instead of sinus omega t, I can write the Euler functions for this. It is this one and divide by factor double j. And so double j it is the constant, so I put before the integrations, and now I can divide into two integrations, and as a result I obtain such value, but we see here j and j, so as a result I obtain the transformation of the sinusoidal functions. Okay, so now I will show you the short table of Laplace transform pairs. Of course, it is not you cannot remember of all this function. You can use some notes for this function per transformation pair. Okay, so we know delta f is fs is equal, if in the fs domain, s domain is equal 1, just 1. But the unit step functions transformation is 1 by s. A e up to minus at is just 1 by s plus a. So it is important when we multiply by this function, we just in the s domain we shift with the same factor. Okay, t we calculated it, so it is 1 by s squared, and t up to n by n. Summation is equal 1 by s up to n plus 1. Okay, and t multiplied by this factor, so it is very similar to this one, but instead of s squared, we should put s plus a and this all to square. And the same, this is a very similar situation to this one. So here we have, without this factor, we have here just s up to n plus 1. And in this case, we have the same result, but with a in the denominator. And the second part of this, or sinus, we calculate it, cosinus transformation, it is quite similar, and sinus multiplied by this factor, we can guess that we, instead of s, we use s plus a here, and the same with cosinus, we put instead of s plus a. Okay, now we are talking about the properties of Laplace transformation. When I show the pairs, for example, we just guessed about this property, frequency shifting. Frequency shifting, so it means that frequency shifting in the S domain. It means that in the time domain we just multiplicate the function ft by factor e up to at. Okay, but first, magnitude scale. When we have the factor a for ft, we have the same factor in the S domain. The second property, additions, subtractions. When we have the two functions, when we want to add the two functions in time domain, it is the same for S domain. And time scaling. So when I just change the scale in time domain, it means that we must change the scale in this reason in S domain. And time shifting in time domain, it means that we have to multiply by this factor transformation. So in S domain, we just have to multiply by this factor. So it is similar to frequency shifting, but here we have the similar factor, but in the time domain. Okay, and differentiation in time domain means the multiplication by s or by s square, etc. in the S domain. Multiplication by t in time domain is differentiation. It is differentiation in S domain, and division by t. It means this we can calculate this integral in the S domain, and integration in time domain means the dividing in the S domain, and the last one, it is the convolution. The convolution in time domain means the multiplication if in the S domain. And now we can try to use some properties to find Laplace transformation. For example, the first one, we have also this function in the table, but we know that, for example, we know the transformation for this one. And when we using the property number 5 with frequency shifting, we just write instead of s plus a in this situation, and we know the transformation of this original functions. So we know here about the cosinus and about the properties, and when we combine this one and this one, we obtain these results. And so the property number 8, it is the division by t. For example, sometimes we know the transformations, such functions, and but we need the find the transformations without this t, and this t multiply by divide by t. So when we use this property, we know these transformations, and when we make this integration, we obtain this value. And now I check it, for example, for g functions, and when we look at this transformation of transformation e up to at, it is just the same results, 1 by s plus a. So it is a demonstration of property number 8. Okay, and now we can try to solve the equations using the Laplace transform, and we have these equations in the time domain, and we want about the initial conditions, and we can apply the properties number 6. It is connected with differentiations, and number 10 connected with convolution. And differentiation, we know that differentiation in the time domains means it is the multiplication in S domain. So instead of this, I just multiply by S in S domain. And I can also take to account the initial conditions, but initial conditions is equal 0. So I have here only the first. And this transformation, it is we know about the magnitude scaling. So this magnitude is the same in this situation, and this one is connected with the convolution and the time scaling. This is the time scaling. So we have here the s plus 2, and at the end we know about the step unit functions, which is 1 by s, but the magnitude is equals 10 here. So as a result, I obtain the Laplace transform such functions. Okay, but we have the solution in the time domain, but for me this is interesting. It is the functions in the time domain. And functions in time domain is obtained by performing the inverse Laplace transform. Okay, and now I give you some information about the Laplace transformation of periodic functions. For example, briefly, for example, we have such functions, and we can write this transformation just by f from s. Okay, and now I put here for this function for one period, and it can we write as ft, and we know that this one and this one, when I subtract from this function and obtain this result, and for using the addition subtraction property, we know about this. Okay, so now I subtract this function, and so I have here the f of from t minus big T, and these unit step functions, and I, as a result, using the property connected with the time shifting, I obtain this results. And the end, the transformation of periodic function, it is the transformation one period divided by this factor. Okay, and now it is the moment when we're talking about the inverse transfer. Maybe at this moment I make the short break for 10 minutes. Okay, so we start 10 15 past 10. Okay, so
Niggas.
Okay, welcome again. I talk with the people from the condition film company. So they have a break up to 11. So I think now it will be better. Okay, so inverse transformation. So the procedure to use the Laplace transformation to circuit analysis is given below, and I told you about it, but we can summarize. So first step, we make the transform the problem from the time domain to the complex frequency domain. So it means the S domain, and solve after this. Solve the circuit equations algebraically in the complex frequency domain, and at the end we just make transform to the solution from S domain back to time domain, and all lectures connected with this, how we can make this in the electrical circuit, it will be in the next week. So now I talk what is the solution, how we can return to time domain from S domain. Okay, so algebraic function of the circuit equations in the complex frequency domain, maybe you noticed up to now, that it is the results we obtain as a rational function of this. So we have some polynomials here, and so the roots of polynomial fps are called the zeros of function f is, because at this value function f is equal 0, and so we have the zeros of these functions. Roots of this function ps is are called zeros, and we have here also the qs, and the roots of polynomial qs are called poles. Since at this value of s, functions fs becomes infinite. So it is important that we know about this. What is the zeros and poles of function fs? So we can try to remember that the zeros is connected with the denominator and poles connected with the denominator. Okay, and if f is a proper rational function of s, then is with the condition is when n is bigger than m. In the other case, we can divide p by q to obtain a quotient reminder that is right here. After that, this p divided by qs is a proper rational function of s. Okay, and we have several forms of the roots of qs, and the roots of qs are more interesting from us, and n is bigger than m from these rational functions. And so we have three cases. And first one, simple poles. If the roots are simple, this p by q can be expressed in partial form as these equations. And we have such some factors k1 up to kn, and we have here in the denominator s plus p1 up to pn. And for all of this, I give you examples, of course. And now we can take into account complex conjugate pairs, and QS has a simple complex root, so they will appear in complex conjugate pairs. The conjugate is right by this asterisk, and we have here the conjugate. It's here. We have minus and we have the plus. And as a result, and the third is QS has a root of multiplicate R. So it is a similar situation to the first one, but here we have the same value P, but we have the power here is 1, 2, up to R. Okay, and the importance of those partial functions expressions stems from the fact that the function f is expressed in this form. The individual inverse Laplace transform can be obtained from known and tabulated transform pairs in these cases. Okay, and how we can find the factors, for example, Q1 up to Kn. So the constants key I can be computed by multiplying both sides by S plus P and evaluating the equations at this point. So when we know this factor, for example, P, we must inverse this and solve these equations for this. So firstly, multiplicate by both sides by this, and so as a result, we obtain only the one constants at the right, and on this opposite we have here this polynomial, and multiply it by this. And when we know all these constants, we change to the functions from S to the domain, and we can obtain using Laplace transformation pair for this. So this one is it is the factor, and in the denominator we have S plus something, and this means that it is connected with property with frequency shifting. So frequency shifting is this domain. It means that we have the time. In the time we have to multiply by this factor. Okay, and this is the example. For example, we have such functions, and we see here the some factors in the denominator, and we want to find ft, and we write this formula to this one, and we can calculate the factors. And first factor key 0 is find for when we multiply by both side by s. So from the left, this is disappear s, because this s and this s is divided, and now we have here s, and s in the denominator, and now we put s equal 0, and this result we calculate. As a result, we have here 0, 0, and 0 for the right, and just we have only the key 0. And on this one, we have here 1 and 3, and this is the values in the brackets, 2, 4, and 5. So as a result, we obtain 9/10. Okay, and similarly, we make for the we should do for the second factor. Now we want to calculate the key one. So for key one, we must we have to multiply both sides by this factor. Okay, and after this, when we multiply by this factor, we put -2, because for -2 it is equal 0. And at the results, we obtain this factor, and the same for factor key 2 and key 3. So as results, when we put this function and the constants key 0 to key 3, we obtain such equations. And in the time domain, we use the property about addition and subtraction. So we change to the time domain each part separately. So we know that for this we have just only the magnitude. We have here the shifting in time by this factor and this factor and this factor, and of course it is also for from 0 up to infinity. So I will put here the ut function. Okay, and similar situation is from another. Assume that f has one pair of complex conjugate pairs, and the partial equations for this is can be write by these equations, and also we can use the same manipulation. We can determine the Q1 in the same reason, and as the end we obtain this result, and the corresponding time function with this complex number is when we calculate this function, we obtain we can change the form from algebraic to the exponential, and when we have the exponential form of complex number, we can use here the Euler identity. As the results we obtain from this the cosines from this. Okay, so we know that when we have such form, as a result in time domain we obtain the periodic function cosines. Okay, and now the example. So we can rewrite this part of the denominator as s plus 2 minus j, and the conjugate for this, and s is of course the same. So we try to now we try to find this factor and the factor Q1 and its conjugate. So for this one, we multiply both sides by s. Of course, it's disappear. This s is disappear in this situation, and this is 0, and 0, and the result we obtain the number 4. Okay, and now we try to find the Q1 factor. and for Q1 we must multiply by this one, and for on the left side I have this, but on the right side only the Q1. And when I calculate this, when I put instead of S this value, I obtain -2 minus J, and I change this form of complex number to the magnitude and phase. And of course, we know about the conjugate is the same amplitude, but with the -5 phase. So it is opposite phase. Okay, and as a result, we obtain this function in the S domain, and in time domain we change this separately, and this one gives only the magnitude, and for this one we have the multiplication of amplitude here because of this, because here is the double, and here is the double amplitude this, and here is the factor 2 from this one, and this is the angle here. Okay, and so we have the function ft, and the last one, multiple poles. It is such functions. We can write these equations in the S domain as summarize such one. For example, here we have s plus p square, etc., etc. So we are employing the approach for a single port information. We can evaluate key one is in this key 1r, and this for the same. We just multiply both sides by this value. We start from the largest value of r, and now we put instead as minus p, and we obtain this factor. And this factor with so we start from the largest value of r, and the second one we obtain using the derivatives in the derivatives, and we must derivative this left side, and as a result we obtain this factor and the same, and we should do this for the last factor with the power of with the power equal 1. Okay, so it depends how many times we make it. Okay, and for example, we have the function like this, and now we can try to find the transformation, inverse transformation. So we can express this function in a partial fractions. Of course, it is this is the simple key to it is the separately because it's not connected with the powers, and this one we have the 3 here, so we have the three partial fractions connected with the first, second, and the third. Okay, and firstly we try to calculate this factor. So we just both sides multiplied by this factor. As a result, we put here minus 1 from this pole, and as a result, we obtain the 20. And now we try to find this factor. So we must we have to do here the differentiation, and when we differentiate this and put here the -1, we obtain this factor. So the result is here. So this is the result of differentiation, and when we put -1, we obtain this factor. And the same, the second derivative for the key 1, 1, and the result we obtain the number 10. And at the end, we find from the theory connected with the single pole, we calculate the key 2. At the end, we obtain such function. So of course separately. So this is connected with the first one, the second one, and the third, and the last one. This one and this one is similar, and we know that the differentiation in S domain is it means that the multiplication by t in the time domain from the properties of the transformation. Okay, and this is the reason how we can return from the S domain to the time domain. But it is when you try to do, you maybe notice that it is not obviously in all cases, because it is for someone functions it is a good idea, because we know okay, so this function is the conjugate poles or single poles, but in the other cases we cannot do this. So there is another concept which is connected with property number 10, convolutions. So convolution is very important concept and has wide application in circuit and system analysis. You know from this table which I presented that the convolution in time domain is equal the multiplication is in the S domain. Okay, and convolution is given by the equations, integral equations in time domain, and this term is it is the symbol of convolution. And so we have the Z transformation ZFS, and separately the transformation these functions and these functions. So when we describe it by convolution in time domain, we just know that in the S domain it is only it is just a multiplication this transformation. Okay, and so the important information, convolution in time domain corresponds to multiplication in frequency domain. And according to the definitions, so now I put the definition of convolution to the definition of Laplace transformation, and some conditions connected with the step functions. So we can try to prove that it is true. Okay, and so when we calculated this, so these informations, it allows to change the upper limit of integrations. From now, instead of t, we have here the infinity. So when the upper limit of integrations are the same, we can put this function before the brackets, and we know about this that this is just time shifting. So when we use the property number 4 connected with the time shifting, we just obtain that it is the f1 with this factor, and the result we have here the first function, and here we have the second function. So as a result, we obtain the multiplication in the S domain. And we have some properties of convolution integrals like communication, connections, separation over addition, and multiplication by constants. And it is collected in this table. So and here I put some functions to show you what is the convolution, and we have the first function and the second function, and for the t less than 0 and another tau. Later tau, these functions are separated, and the sense is only from t more than 0. So here we have the information that here we have the 0. Convolution is equal 0. This from t less than 0, and it is not 0 from this region. Right? Okay, and transfer functions for network for the circuit is given by expression. So the example of using the convolution integral, and transfer function, it is the ratio, the output to the input in the S domain. So transfer functions for network is given by this expression, and in this case, you see in this example we have 10 by S plus 5. So the input function is a step function Vs. So we have here the Vs, and find the output voltage using the convolutions. So we now I show you the two different methods for calculate the voltage output. And first of all, we know about the transformation of this. We transform HS to HT, and we know that is the shifting. And now we just convolute by this HT and this VT. And so we try to calculate the convolution, and now we have the 10 and this factor connected with this function, and we know that 1 by S in the S domain is just equal U t in the time domain, and this is the constant, and of course U t in this region is equal 1 in all region, and in the results we obtain such value for this, and it is the time. It is the signal in the time domain. Okay, and for comparison, determine the same value using the partial fraction expansion method. So now we don't know anything about the convolution. And we just using these equations. So V0 you can calculate as a HS multiplication by this one. We know about the HS and multiply by this one. So we can find the factor key 0 and key 1. As a result, we're using the partial fraction expansion method. and on results we obtain the first and the second constants, and as results we obtain such value. So we know that this one is connected with amplitude, and this one it is the same amplitude but shifted in with the factor 5. So we put 5 minus 5 here. Using the frequency shifting property. So we obtain the same results here and here. So using the convolution and using the second method, partial factor expansion, we obtain the same result. Okay, and the convolution seems very complicated, but it is very powerful and useful for. So convolution permits us to obtain the network response for input that cannot be written in analytical functions, but can be simulated on a digital computer. And I show you how we can calculate using for example, the lab view for this. But now another examples. So now we have the linear circuit. For example, we have the bandpass filter. This is, for example, the black box. We don't know anything about this circuit, and we need to determine the HT. So we can measure the response VT for knowing V input. Okay, the obvious options for this is the delta T, because transformation of delta T is equal 0. So for when we obtain the output voltage for delta T as an input, we just have the HT. But it is in laboratory impossible. It is impossible because we cannot generate the ideal delta T. Much easier is using step functions. So let's assume that as an input functions is 10 multiplied with is the step functions with magnitude 10. So as a result, we have the output voltage is in S domain, and instead of VE we put 10 by S, and when we want to find HS, we have just V output multiplied by this one. So according to property number 6, multiplication is S domain is derivative in time domain. We use this property. So we know that the HD, it is just derivative output voltage multiplied by this factor. Okay, and so when we want to obtain the HT, we just derivative of the filter response to the step input. And in the laboratory, it is not very complicated because we can apply the voltage from generator and measure V output using the digital scope. And from the digital scope, we can collect the probes and the data. For example, in the text file, etc. And when we have the samples, we can make the derivative from simple algorithm. Just this is the most simple algorithm for calculate the derivative using the next sample, the current sample, and the time sampling. So this is the distance between these two samples. And for example, when we have the HT, we can test our model using another source. For example, we have a source like this here, and in this region of time. And to find out, we must convert this one and this one and the results. So firstly, to summarize, firstly we find the functions gt and from the knowing source, and when we have the functions gt, we can change the source, and we can calculate the response for this signal. And this is the output input signal. Here we have this signal is on the input. So for example, we know that the offset is about 4, and this signal is from 0 to 25 milliseconds. After 20 milliseconds, this signal is going to 0, and this is the response of our filter. Of course, the response is much. The time of response is much bigger than the input. Okay, and now I because this example is with the black box. Okay, but now I would like to try show you the real example. So we can take to account the low pass filter. This filter is connected with which consists the resistor and just capacitors. And this is the value of resistors and capacitors. This value is good for calculation point of view. So we can calculate the HS functions that transfer functions for this as functions V0 to divide by V input. And the results we obtain such functions. Okay, so we can transform this to the time domain. It is very simple, because here we have the magnitude, and this is the shifting in time. Okay, and we can use another program and another environment to calculate. For example, it's a good idea to use MATLAB. I know that you know MATLAB, for example, or something else. For these calculations, I use the LabVIEW. Maybe you hear about the LabVIEW. And this is the LabVIEW. It is also this is the environment which can allows us to make some calculations and using the digital cards, and it is good for presentations. And this in this environment, we cannot worry much about the graphs, about the panels, because it is divided naturally to two parts. We have the panels and we have the diagram. So here we have the panels when we can make anything. For example, we can put some knobs, some displays, etc. So this is the interface with the user. And the second is the block diagram. So now I switch to the block diagram, and in the block diagram I use the two basic generator, and this this h function. So here I calculate the h functions, and now here I have the signal, and now I convolute using this block. And maybe now I switch to the presentation. Okay, and so we have here the input voltage. So this is the two sinus functions with another amplitude and frequency. So the first signal has frequency equal 100 Hertz, and the second 5,000 Hertz, 5 kilohertz. As results, when you combine two signals, we obtain this sinus, slower sinus, and the modulations with this frequency. And when we use this one, so we start here, and as results we obtain the here we have the source, and this is our HT functions connected with our circuit, and the results we obtain just only the almost only connected with slow fractions, because it is the low pass filter. So we filter this and as results we obtain this one. And also I want to show you it is, for example, try to switch to another program. Okay, and so okay, so now I'll share again. Okay, so I try to show you the same example in the PSpice briefly. So I have the schematic, and I have the two sources, and this is the low frequency source with the same amplitude as in the presentation, and this is the source with the higher frequency, 5 kilohertz, and this is the capacitor and resistance. Okay, so we can make the transient analysis, and so this is the analysis, and now we can observe the results of this analysis. So I can add plot, plot and trace. So this is the, now you see the source, and so it is this amplitude. And notice that this amplitude and this amplitude is the same. So you remember about this amplitude of the output. Okay, and now switch to the SPICE. Okay, now I add the trace connected with the output. Okay, so and we you see here the output, and the amplitude it is here about 2 volts. Okay, and we can observe this one also using the Fourier transform, and so we change the time to the frequency domain, and in the frequency domain you can observe that for the this frequency, for low frequency, equals 100 Hertz, the changes are small, and for 5 kilohertz, the changes are very big, because from this amplitude is changes up to this amplitude. So maybe I can first I can change the scale, and so from this amplitude we change this amplitude up to this value. So our field is quite good. Okay, so you can see these results also here, and at the end, three slides: initial value and final value theorems. So the initial value, sometimes it is not initial theorem you use for calculate our behavior of our circuit at the end at the beginning, without calculation the transformation, maybe not transformation, but without calculate the inverse transformation. So the initial value theorem states that limitation for ft when t goes to the 0, it is equal the limitation for s going to the infinity s multiplication by the transformation of function ft, and provides that ft and its third derivatives are transformable. So this is the assumption. And the final value theorems is very similar, but here is the limitation. Another limitation: here we have the infinity, and here we have the 0. And of course, the very similar assumptions. For example, let us determine the initial and final value for this function. We have the function, and we use we know that the corresponding time function is equal by these equations, but of course, when we use the final and initial values, it's not obviously, but it is only for check it, this theory. And applying the initial value theorem, we have that at the point 0, when we calculate this limit, we obtain just this function, because the s is disappeared, because I might multiply by this s, and it is equal 0. And the poles of this function is on the left side of the s plane. So in the next week I talked more about it. So the final value term is applicable. Choose. We can know that steady state, so in the time equal infinity, we obtain the value equal 5. And so we can also change this value directly from this function. When we put here the t equals 0, we obtain that from the 0 we have the ft equals 0, and from the t equal infinity, this is equal 0, so we obtain 5. Okay, and so thank you for your attention. I'm sorry for the noise. Of course, I put this presentation on the Dropbox. I give you also the link to the book, and so goodbye.